Hi, my name is raniti-umd, and today I will be sharing or presenting about a project I worked on as part of a course titled Autonomous Robotics, which I'm taking at the University of Maryland. This assignment was called the Grand Challenge, and it's really the main project for this course. So a little bit more context. This course is all about putting together a robot from component parts, sensors, actuators, robot chassis kit, etc. So it's really about integrating those parts, building software, and getting the robot to achieve a certain task. So what was that task? Well, it was basically to get the robot to navigate an indoor, flat, 10 foot by 10 foot arena and find these different colored blocks, which resembled like construction materials on the Martian surface. So to find these blocks and to transport them to what we call the construction zone, which is basically a particular location on the 10 foot by 10 foot arena, basically the top left corner of the arena, a 4 foot by 4 foot square. So what I'm going to do now is briefly introduce you to the hardware and the software concepts that I put into practice on this project. So in terms of motion and tracking motion, we have 4 DC motors actually powering the 4-wheel drive of the robot itself. We also have a servo motor integrated into a gripper assembly that is actually doing the clawing or the gripping of the colored blocks and transporting of the colored blocks from their initial positions to the construction site. In terms of sensing, we have what are called the proprioceptive sensors, and then we have the exteroceptive sensors. The proprioceptive sensors being responsible for tracking sort of like the best guess of the robot's dead reckoning, and then we have the exteroceptive sensors responsible for looking out into the environment and recording that data. So in particular with the proprioceptive sensors, those were the inertial measurement unit which tracked robot yaw or heading angle, and then there was the pair of optical encoders which were used to track wheel rotations on the left side and the right side motors. In terms of exteroceptive sensors, we had a Raspberry Pi camera module, which was used to track the locations of the colored blocks relative to the robot, and then we had an ultrasonic distance sensor, which was used to detect proximity to the walls of the arena. I will say that this robot was also built on other hardware as well, the main computer being Raspberry Pi Model 4. Also, we use an Arduino Nano microcontroller unit, which had the specific purpose of interfacing with the inertial measurement unit via I2C communication protocol, and then interfacing with the Raspberry Pi via a serial connection. Other hardware existed on the robot as well, such as a motor drive H-bridge unit, which allowed me to change the direction of the left motors and the right motors, and then also to command different speed levels via pulse width modulation. As we prepare to walk through the robot codes, I want to actually share a series of figures to serve as mental models. The first being the map of the arena, showing the landing zone, the scattered blocks, and the construction zone. So next we have a diagram demonstrating the notion of reference frames, as is pertinent to this project. So I define a world fixed reference frame with origin at the lower left of the arena. I also define a reference frame fixed to the robot itself. That is a body fixed reference frame described with 3 coordinates, x and y for translational degrees of freedom, and then we have psi, which tracks the rotational degree of freedom. Psi basically represents the angular displacement between the body fixed y coordinate direction and the world frame y coordinate direction. Next up, we also have what is a discrete motion model. The codes are basically based around this discrete motion model. This is essentially state update equations. We have the state being a function of the previous state and a function of the controls, which I'll talk about in a moment, and a function of uncertainty, which I'm abstractly conceptualizing as a vector epsilon x, epsilon y, and epsilon psi. For the controls, we have a delta r, which is essentially a distance command to go either forward or reverse a certain number of feet. And then we have a discrete psi command, which describes a pivot angle. These controls are linked to what I would call the motion primitives of the robot. By the term motion primitive, I mean to say that I have implemented the code such that the robot can only move in one of these 4 ways at a time. So it can pivot left or right, and then it can move forward in reverse. The pivot commands are integrated with IMU sensor feedback, and then the forward and reverse commands are integrated with encoder feedback. Two mental models remain that I'd like to talk about before I get into the code. These mental models really give you an idea of the actual Grand Challenge strategy that I ended up adopting. So this first mental model is all about perception. It's all about getting the robot to detect and then drive towards blocks of the target color. So this represents a frame captured by the Raspberry Pi camera. What you'll see in my code is that I use a series of image processing steps, such as HSV masking and contour detection, to identify blocks of a certain color in a frame. I will then basically identify the center of the detected contour, or the highlighted contour, and I will count the number of pixels between the center of the image and the center of the contour. That'll give me what I would refer to as a pixel error. And it's a signed pixel error. To the right is positive, to the left of the image, center would be negative. So what I do with this pixel error is I actually convert it to a pivot angle command using a calibration ratio, which our professor has kindly provided to us. So in terms of image processing and perception, I will make a note that I spent some time determining proper HSV masking parameters by taking many pictures with the Raspberry Pi camera, and just through trial and error figuring out the best HSV bounds to use to reliably detect red, blue, and green. So after conducting steps to test out my HSV masking parameters, and once I was getting reliable results from that, I went on to pay attention to the way my pivot left and pivot right motion primitives were working. So they didn't seem to always actually pivot to the commanded angle, and it wasn't a matter of overshooting by a couple degrees. It was a matter of sometimes the robot would just keep spinning. So at first it was very confusing as to why the robot was exhibiting this behavior. I eventually did some research on the internet and learned that the IMU was basically taking readings at a very high rate and stuffing them into what's called a buffer, which is like a first in, first out queue of sensor readings. And what was happening was, the way I had my code initially was that I was using just whatever the next sensor reading was that came off of the queue. And oftentimes that whatever sensor reading was very stale. By stale, I mean it was taken several milliseconds ago, or tens of milliseconds ago, or longer. And the fact that I was using such stale reading in my control loop was making the logic that I had already implemented in that control loop irrelevant, leading to that unexpected behavior. So what I ended up doing was implementing this routine where my Raspberry Pi would send a particular signal over serial communication to say, hey, I'm ready for a reading, please take one. And then only then would my Arduino receive a sensor measurement from the IMU and make it available over the serial communication line. Once I made that fix, my pivot command became reliable. So what I'm briefly going to do is describe, finally, the basic gist of my code base. So it was entirely written in Python, utilizes libraries like libcam2 and Raspberry Pi, GPIO, and NumPy, and OpenCV. And it's just organized into an assortment of classes, each sort of encapsulating something different but important, such as the vision class, which handles the computer vision pipeline, contour detection, HSV masking, identifying a block of a certain color in an image, estimating the pivot angle to that block. Then I have other classes like the moves class, which handles where I implement the motion primitives, and you can see how the control loops depend on sensor readings. For example, pivot left has a control loop which depends on IMU readings, and the forward motion primitive and the reverse motion primitive rely on encoder feedback. And then another important class would be a class I named Travel, and Travel is basically a class responsible for tracking the state estimates throughout the mission. And I'll be uploading all of this code to GitHub for your more detailed and thorough review. This is just the gist of how it's structured. So, unfortunately, my robot performed in a rather underwhelming way at the Grand Challenge, collecting only one block, transporting it to the construction zone, scoring a point, but then crashing into the north wall of the arena. So the bottom line reason for this underwhelming performance was I actually didn't implement the plan I had in place for my robot, and this was due to timing constraint and the fact that I was very new to putting a robot together from component parts and programming its software. So when I say that I wasn't able to implement the plan I had in place for my robot, I mean to say that I was not able to implement the full or complete plan I had in place for the robot initially, whereby I would track the robot pose with a dead reckoning approach, but then also incorporate a relocalization step based on ultrasonic distance sensor readings, whereby each time the robot arrived at the construction zone, it would do a spin around and estimate its distance perpendicularly to each of these walls. Then with those measurements, get a new estimate of its translational, or XY, coordinate in the fixed reference frame. And use that XY coordinate to essentially replace the dead reckoned estimate.